Good afternoon to everyone. And first of all, I want to thank all of you for your interest in the SIMTAP project. I am the responsible, together with Professor Carlo Bibbiani, who is one of the speakers today. Of course, I thank the European Society for Agricultural Engineering for hosting this workshop, which is included in the satellite activities of the conference of the Society this year. I also thank very much Professor Daniele Torreggiani and his collaborators at the University of Bologna, partners of the project, who oversaw the technical organization of the webinar. The title of the seminar is clear. It is not necessary to explain its goal. However, before giving the floor to the speaker, I want to briefly illustrate the SIMTAP project. Before of that, I pass the floor to Daniele for some technical information about the webinar. Then I will show you a few slides to introduce the SIMTAP project, and then we start the scientific session. Please, Daniele.
Thank you very much, Alberto, and I would like to say welcome to everybody and thank you for attending as well. Thank you, Professor Paradossi, very much for accepting the proposal of organizing this workshop within the EurAgEng conference. And we as agricultural and biosystems engineers are really proud, first of all, of course, to be part of this very, let's say, exciting European project. And of course, we are also very proud and glad that this workshop is going to be held within the framework of our International Conference of Agriculture and Biosystems Engineers in Europe. So we would like to thank EurAgEng for hosting us within their program. That's it. So thank you very much, Alberto, and I look forward to listen to you and all the speakers. Thank you very much.
Thank you, Daniele. Thank you. So just a few words on the SIMTAP project. The project was approved in November 2018 as a part of PRIMA, Partnership for Research and Innovation in the Mediterranean Areas, the call of 2018. The project officially started about 2 years ago, 1st June 2019. The project is coordinated by myself and Professor Carlo Bibbiani at the University of Pisa. 7 other partners, they are shown in this slide, are in Italy, France, Malta, Turkey, and Germany. Most of the team leaders are among the speakers today, including the team leader of INRAE now, in France, Dr. Joël Aubin, who unfortunately is not able to attend the meeting, but has sent his presentation, slides with audio, a couple of days ago. INRAE represented today by Dr. Aurélie Wilfart. Thank you, Aurélie. Just a few words on the conceptual framework of the SIMTAP project. The project has its focus on a closed-loop multi-trophic seawater aquaponic system for the production of sea fish and plants for fresh consumption or for industrial processing, for instance, for the extraction of active ingredients of nutritional or medicinal interest. The fish in the system, the fish will be fed with algae, worms, and mollusks, or other detritivorous or filter feeder organisms, DFFOs, producing the SIMTAP in partial or total replacement of traditional feed based on fish oil and fish meal. Actually, the system integrates an aquaculture system with an hydroponic cultivation of plants, which are capable to grow and develop at salinity levels close to those of seawater. The SIMTAP system consists of different cultivation units for primary producer, algae, crop plants, halophytic species or halo-tolerant glaucophytes, breeding units for DFFOs, fish tanks, along with a biofilter. All these units are interconnected in a closed system that is with the recirculating seawater. For instance, the salinity in the system we are using a study in Pisa in Italy has a salinity of 25 grams per liter. According to this conceptual schema, wastewater and products from one level of the multi-trophic chain are recycled and used, becoming the inputs for another level. The objective of the SIMTAP system is project is to evaluate to what extent an integrated diet with algae and DFFOs can replace the traditional feed consisting of fish oil, fish meal, and other ingredients, which has a significant environmental impact due to the overexploitation of fish resources and the intensive cultivation of cereals and legumes. The filter feeders organism, along with the algae, represent a suitable source of protein and polyunsaturated fatty acids, alternative to fish meal and fish oil. Other goals of the SIMTAP are the reduction of waste material originated by aquaculture system and discharged to the environment, for instance, wastewater, and the use of water runoff from greenhouse crops, which are still rich in mineral nutrients, for instance, nitrates and phosphates, and can be used for algae culture in photobioreactors. These photobioreactors produce low salinity nitrogen-free water and biomass, which can be used respectively to compensate the water evaporation and to feed filter feeders organism in the SIMTAP system itself. Moreover, the project aims to evaluate the effectiveness and performance of SIMTAP system in terms of food production and use of energy, water, and other resources. Life cycle assessment, analysis of energy consumption, energy assessment of the SIMTAP system will also be performed to quantify the potential environmental impacts as compared to conventional hydroponic and aquaculture systems. Another crucial issue, of course, of this project is the economic assessment. The project has 8 work packages, as shown in this table. The project activities are delayed due to the pandemic, especially in 2020, and at the end of the project, scheduled for the spring of next year, will almost certainly be postponed by 1 year. We are now, therefore, halfway through our project. In the first part of the project, the main objectives are those shown in this slide. In this seminar, indeed, we will report the main results achieved in 2020 and spring of this year. Just to show you some outputs of the project so far, this is a list of the publication. Several manuscripts are in progress or have been already submitted to international journals for publication. Finally, I show you a list of some dissemination activity performed during the first 2 years of the project. Due to the COVID pandemic, all the events took place online, and this offered the advantage of being able to record and post the full recording of the presentation or interview on the internet, especially on YouTube. As I told you, just a few words on the project. It is the time to finish my presentation, and therefore, after thanking you for your attention, I pass the floor to the first speaker, Professor Carlo Bibbiani of the University of Pisa. Please, Carlo, go on with your presentation. Thank you very much.
Hello, good morning, everybody. Good afternoon, sorry. And I want to thank you, the hosting Congress of EurAgEng, as Professor Torregiani has already said before, but it's a great honor to be in this Congress as a workshop. So I'm going to show you the SIMTAP prototype built in Italy at the University of Pisa. That is one of the Italian partners, and where the coordinator, Professor Pardossi, belongs as well. I belong to the same institution. Here you can see the group who is working on the project. There are many researchers, young researchers, and some professors, and is a very, very nice group research group working on this important project from our side. And I'm going to talk about the objectives and the design and preliminary results of the SIMTAP system in Pisa. So, first of all, I want to make a step backward, talking about the conceptual framework of the recirculating aquaculture systems. That is, as you know, one of the most interesting system to cope with the production and the rearing of fish in land-based system. The recirculating systems can recirculate on a daily basis more than 90% of the water circulating in the system itself. And this is a good result, but we have to improve this result, aiming to a better environmental concern. Concerning about the wastes produced within these aquaculture systems. As you can see, the main units of these RAS, recirculating aquaculture systems, are, of course, the rearing tanks, and then we have to remove the suspended solids and other byproducts of the rearing by some devices. So we have mechanical filters, bioreactors or biofilters, and the gassing units, and of course some disinfection against diseases. How can fish wastes be removed? As you can see, up to 25% of the feed given to fish can be found in the water as suspended solids. And but much of the nitrogen produced is excreted in the form of ammonia. But phosphorus can be found in sedimental solids. And the solids are really small in dimensions. That's the problem. So all the devices that are used to remove these wastes are really hard to be run. But of course, there are other balances that can be taken into account. Rearing live organisms such as fish and bacteria needs a strong supply of oxygen, and removing all the byproducts of the rearing, such as the nitrates converted by the bacteria, and all the CO2 and the ammonia itself. Of course, you have to remove the fines and coarse solids. So there are many devices, as you can see from these pictures, in a RAS system. What about the RAS future? Up to now, for example, in Norway, where the aquaculture industry is really well established, as you know, there are a lot of projects to move the salmon aquaculture from sea cages to land-based system. More than 50 projects can be found at the moment, aiming to move up to 25% of the production before 2030 in inland-based system. The costs are, of course, higher. We can, based on this study, you can see by Intrafish, roughly 40% more can be, the cost can be more than 40% as sea cages aqua farming. But what about the future? So a step forward, a very promising system are the integrated multi-trophic aquaculture systems. As Professor Pardossi said before, the project SIMTAP we are talking about is an IMTA system that has some other objectives that I'm gonna show you in a while. So the name self-sufficient refers to producing fish feed, but also the sustainability of the aquafarming industry, and refers to the reuse of brackish water and runoff waters coming from other agriculture compartments, such as greenhouses, cultivation, runoff. You have already seen this picture, so I skip it because I'm gonna show you some more details in a while. But before showing the pictures and what we have built in Pisa, I want to clear out some boundary conditions that are the environmental conditions that we have here at the University of Pisa, because our system was built inside a greenhouse. So our main concern, as it is a research project, is to cope with high temperature related risks. So we installed also a heat pump to control the water temperature. Of course, it's very costly, but we have to test this very extreme location for an IMTA system. And another concern is about the target technology level of the system. Our target level is intermediate, so we don't want to have very high technological devices removing all the wastes I talked before. At the same time, we want to assess the possibility of having an IMTA system that is using some deposit filter feeders organisms in the system, to what extent they can remove some wastes from the water, balancing the system itself. So we are testing the substitution of drum filter with a large surface settler. That is the deposit filter feeders unit. And the other task, the other simplified solution is avoiding the skimmer presence in the system itself. Again, the skimmer can be substituted by the filter organisms. So let's have a look in detail on the units we built at the University of Pisa. We have, it's a small system, so it's for research purposes. We have 6 fish tanks, around 0.6 cubic meters each. And the water flowing from those tanks goes to the deposit filter feeders unit that are 9 tanks of 1 square meter each, where polychaetes, worms, so the feeders organisms are settled. So those polychaetes are reared in those units within the filters organisms that are mussels and oysters. The water flows to a sump and another small settler, and then flows to the biofilter or bioreactor. As it's a main loop of the water circulating in the system, the water flows to the halophytes or glycophytes unit where we can rear plants, crops, and we can rear also macroalgae, namely ulval rigida. Beside the main system that I show you, we have a side hydroponic system hosting plants cultivated on runoff coming from crop greenhouse culture, from other greenhouses crops. And we have also the microalgae unit that are, we can say, a sort of the engine of the system, a sort of fuel, sorry, of the system, because from the produced biomass by microalgae, we can rear polychaetes and mussels and oysters, and so we can produce our own feed. We have, of course, water pumps, air blowers that are really important, and UV lamps for disinfection, and as I told you in advance, a heat pump. Here you can see some pictures of the fish tanks with fish inside, the polychaetes and filters organisms, the plant units. Here you can see the Salicornia, we are talking about that in a while, the mussels and the sand where polychaetes worms are hosted. And here you can see the microalgae system. It is a very simple system because there are some plastic sleeves where water with microalgae is put inside. As I told you before, we need a degassing unit. In this case, we have some pipes with small bioballs inside that can make a turbulence of the water, removing gas such as CO2 or ammonia. Another important aspect is the control device, but our colleagues from University of Bologna are going to talk later about that. So I skip this important aspect of our project. As we faced some failure of the system due to a blackout of the grid, we had to install an emergency electric generator, and that is a standalone generator, of course, with fuel inside, that can supply energy within seconds due to a blackout of the grid. And it's a really very important device. But let's talk about let's say, our water environment, because as you know, IMTA systems are an evolution of aquaponics, because we have, beside fish and plants, we have also detritivorous and filter feeders organisms, and of course, all these organisms have different requirements in terms of environment and chemicals that can be tolerated by each species. There are some main differences between freshwater aquaponics and marine aquaponics. That is one we are conducting experiments on. The main concern is about the content of some chemicals, chemical elements, such as chlorine, sodium, and other, as you can see, that are quite high respect to fresh water. And so we have to face all the requirements of different organisms, such as plants, bacteria, fish, and worms, and other bivalves, such as mussels or clams or oysters. That is a very, very difficult task, because all the units must be well balanced in the system. So, for example, the bioreactor is a very important device because we have to convert the ammonia excreted by fish into nitrates, and this is you can see the parameters of our moving bed biofilm reactor system. So in our actual system, we can cope to a presence of 30 up to 60 kilos of fish in the system. I want to talk about some results now of our experiments. And here you can see some pictures of the microalgae strains we took from the environment and we cultivated in lab and then transferred to the greenhouse situation. And of course, using the runoff coming from other greenhouses crops, the runoff is not suitable at the best level for growing microalgae, but anyhow, we can reach a good density, microalgae density, as you can see, up to 1 gram per liter, instead of 2 or 3 that can be reached with a good tap medium for microalgae. So it's very important to use runoff because we can take advantage of the wastes of other industrial cycles or industrial compartments, in this case agricultural compartments. And using those wastes, we can grow a very, very interesting nutrient, biomass source for our system itself. That is a main objective of the SIMTAP project. Here you can see the detritivorous organisms. In our case, we used the polycate that is Hediste diversicolor. This worm, we took the worms from the wild and we reared in the system. It's almost 1 year. 1 year we have those worms in our system and they reproduced really well. Here you can see an experiment feeding worms, feeding polycates with chlorella and a special feed. In this case we use mussels, but it can be a standard feed. And as you can see, substituting the feed by chlorella up to 75% and 50% gave the better results. So this is really important because we showed that cultivating chlorella is a good biomass source for polycates. In this case, it is the diversicolor. And in our experiments, the density rose by two times fold, and now we are up to 3 or 4 times fold because this is 1 month before now, and we are more than roughly around 4,000 polycates per square meters. And the biomass density we reached 1 month ago was this one shown, that leads to a productivity of about 70 grams per square meter per month. But now I can say that is a little more. So I might say 100 grams per square meter per month. That is just a good result. Talking about other aspect of our system, of course, the aims of the system is rearing fish, producing fish, for the market, but at the same time we can produce a crop. In this case is Salicornia and Ulva rigida, but I'm going to talk about Salicornia. That is a very valuable crop because, as you can see, the price on the market price is quite similar, or in some cases higher, respect to fish price. We are rearing Sparus aurata, that is gilt-head sea bream. But in the next test, we are going to rear European sea bass as well. About the Salicornia is a very interesting crop, and we did many experiments. I'm going to talk about some of them, of course. And the main experiment is about the best salinity of the water. Salicornia is an halophyte plant, so can tolerate high level of salinity. You can see 0, 10 grams per liter, 20 and 30 grams per liter of sodium chlorine. And so you can see just from the picture and of course from the graph that between 10 and 20 grams per liters, very, very good productivity can be reached by this Salicornia, but also at 30 grams per liter, the productivity is still high. So it can be used in marine aquaponic and can give a high yield per square meters. You can see we reached an average yield of 6.6 kilos per square meters per cultivation, and that is a fresh water, of course. And what is the importance of the crop in the SIMTAP system, in the INTA system? The importance is that can remove the nitrates, so can balance the nitrogen balancing of the system. And so we measured what is the total nitrogen uptake of this kind of crop, this species. And as you can see, can reach up to, this is the total grams per square meters, but in terms of daily nitrogen uptake in our system goes from 0.5 up, let's say 1 gram per square meter per day. And this is a very important parameter because you have to calculate the area for the crop to be given to the crop, just to balancing the nitrogen chemical element. So in terms of commercial feed that can be given to feed, you can see the proportion due to the excretion of ammonia, the ammonia content in the feces and in the particulate and soluble, and the retention in fish. We can make this proportion that 100 grams of commercial feed, standard feed, that is with a very good protein content, up to 54%, can produce roughly 7 grams of nitrogen into the water, can introduce into the water. In our system, so now we are around 33 kilos of sea bream in the system. That is a stocking density of 13 kilos per cubic meter in each tank, and we are feeding a kilo per day. This means that the nitrogen released is about 70 grams, and we should need from 80 to 140 square meters of Salicornia to remove this nitrogen. So the feed crop ratio is between 7 and 13 grams per square meter per day. And at the same time, we should calculate the fish crop ratio, that is 0.25 to 0.45 kilos per square meters. And compared to freshwater aquaponics, you can see that the feed crop ratio is quite lower than the fresh aquaponics. And this is due to the presence of the salt in the water, so the halophyte plants can remove less nitrogen than freshwater crops. So those are some results of our experiments. The last one is that we calculated the substitution of the water. We at the moment we are assessing the water balance, but we reached a water volume discharge rate less than 1% on a daily basis. And as I told you before, the common recirculating aquaculture systems are around 8–10%. So our results are quite encouraging, and less than 1% is I might say a good result. So those are the partners of the project. The squares indicates where the SIMTAP system have been built and are running their experiments. I want to thank you for your kind attention, and I give the floor to the coordinator. Thank you very much.
Thank you, Carlo. Thank you, Carlo, very much. There was a question in the chat about the recirculating water in the system that I replied through the chat, but there is time to explain much better that how the water is managed in the system we set up in Pisa. Please, Carlo.
So, the water parameters are monitored each week for the nitrogen and phosphate content. So we can just control the level of ammonia and nitrate that are really relevant for the life of organisms. They must stay below 1 milligram per liter, as you know. And the nitrates content, that is an indicator of how to what extent the bioreactor works. Let's say that our bioreactor works really well. Sometimes we feed the bioreactors with a strain of bacteria that are provided by a company, a firm that is casually nearby Pisa, not so far away, just 40 kilometers. So we can have bacteria very easily. And sometimes we feed the bioreactors just to keep them working at a good level. Besides this, we set up a threshold of nitrate content up to 400 or 500 milligrams per liter. That is one could say a high content, but as we are running the system since 1 year, we can say that fish are not affected in their health, but by this high content. We have to cope with the evaporation and evapotranspiration from crops, so we add fresh water sometimes 1 or 2 times per week in the summer season, of course. And of course, we have to discharge some water, as I told you before, less than 1% on a daily basis. We don't do on a daily basis, We just do on a weekly basis or every 14 days, depends on the season. But we don't remove any waste from water. We just discharge the water. So in our opinion, this means that the filter feeders organisms units, I show you before, we have 9 tanks, so there are 9 square meters, are enough in our system due to the small fish tank capacity, of course, but they are enough for balancing the wastes, so the discharge or not of those wastes generated by fish. And also, this is an important result in our opinion. So what we are aiming to is to calculate the right surface, the surface of each unit to have a balanced system. And it is not easy because we have different compartments with different organisms. Fish and crops have different, let's say, growth curve. So it's not easy to couple those 2 units as well. But at the same time, we have also detritivores and filter feeders organisms. So we are monitoring all the parameters and we want to assess the balance of the system as a whole.
Okay, thank you, Carlo. Thank you very much.
Thank you.
I think it's the time to pass the floor to the second speaker, Dr. Baldassare Fronte at the University of Pisa. Please, Ubaldo, go on.
Thank you, and good evening, everybody. So my talk is about a particular application necessary for running a production system like SIMTAP is, because the SIMTAP method implies to rethink the production system from their roots until to the fruits, to the products we get. So even those aspects related to the nutrition of the fish must be totally rethink. To this, of course, with the goal to improve as much as possible the sustainability of our productions. The state of art. Actually, when we think about fish nutrition, we use some raw materials, which the main ingredients of aquafeed are those you can see in this slide. And mainly we can remind fish meal, squid meal, calamari meal, krill meal, and fish oil. These raw materials, as you probably know, represent in the past has been representing the majority of the quantity of ingredients contained in the aquafeed. But at the same time, they are related to some environmental issues, which are the sea overexploitations. And of course, the perturbant, the modification of the food chain in the sea. Of course, the highest fish species in the pyramids, of course, are those more affected, negatively affected from the overexploitation of the sea to produce higher quantity of fish meal and fish oil in particular. Other raw materials are soybean meal, gluten meal, corn meal, wheat meal, sorry for the mistake, wheat meal, which are more or less more sustainable, but still they have some negative effect on fish physiology as well as from the environmental point of view. For this reason, we can, of course, work on that to improve the sustainability. Actually, aquaculture is one already, okay, in the conditions, or traditional condition, actual condition. Aquaculture is one of the most sustainable food sector, at least for in the animal production sector. So this is already a good positive news. I mean, it is also why important international institutions, since FAO and the European Union, have been promoting the development of aquaculture. By the way, because the fish meal and the fish oil issue, we can still do something in order to improve the aquaculture sustainability. So this is due, so we have to work for that. So far, in this graph, it's just shown the quantity of marine protein, notably fish meal, which was used in the past. 65% of the aquafeed was fish meal, and thanks to the research in about 20 years, 25, 23 years, the quantity of fish meal in aquafeed is nowadays reduced at 18% more or less. So already something has been done to increase aquafeed sustainability. But we are not happy. We are switching into another dimension, which is aquaponic, which is high MTA systems, and we can, in this case, also try to work to avoid also CO2 produced for the transportation of the raw materials. I mean, the ingredients of aquafeeds. In this picture, you can see soybean, mainly produced in Argentina or Brazil, transported by routes and ships to Europe with the large large consumption of gas and CO2 production. So we can avoid this just if we try to relocate also the production. I mean, we can produce food in the place where the food can be consumed, but at the same time, we can produce in that place also the feed necessary to produce fish or other kind of animals. In our case, of course, our aim is to produce fish, and we are trying to produce feed on site, there where the food production take place. So we are not going to, at least this is our goal, our idea, to import raw materials from Argentina, Brazil, and the USA to produce fish, but we want to produce our raw material, our aquafeed, on site. So this is the context where our trial related to the fish nutrition born. So we were thinking about these issues, and we thought how to produce feed right there where we raise fish. That's why we, now then I will show you some trial very quickly and the experimental design to explain you what we have been done. And I want to show you some preliminary results of our trial. These are some parameters we calculated to measure the effect of the new diets, new generation, let's say, suitable for SIMTAP production. But I think most of you already know this kind of parameters. By the way, I will explain better while we will talk about these parameters. So the first experiment we carried out last year was a really preliminary trial. The SIMTAP system was not yet totally fully completed. By the way, we had the aquaculture unit already working, so we started with some trial on trying to replace aquafeed, the traditional aquafeed, with mussels. Why? Because as you saw during the talk of Professor Pardossi and Carlo, in the SIMTAP we are able to, at least this is what we aim, produce mussels to be used for fish nutrition. So from, as they explained, from the algae, with algae we can feed the mussels and as well as polychaetes, and we can harvest these products to feed the fish. So we started with this trial. So we made 6 different groups in which using mussels we were replacing equal amount of feed, commercial feed. So in the first group we had 100% feed, okay, and no mussels. In the second group we provided to the fish, we supplied 80% of the daily ratio, 80% of feed and 20% on dry matter basis, of course, mussel, 60% feed, 40% mussel, and so on, up to no feed and only mussel. This trial lasted 6 weeks. It was carried out using sea bream juvenile, starting from 5.1 grams, and initial biomass density of 2 kilo per cubic meter, which is not high, but still it was our aim was to detect, to know if such a fresh products, fresh raw material may replace feed. So in the table, better in this kind of graphs, you can see the results. These are the 6 groups, and since the beginning you can have the idea that when we used 100% mussels, the growth was quite lower than in the other groups. Mainly in this other graph, where is represented the final body weight of the groups, we saw, you can see also that when we used 100% feed, the growth was higher than only mussels. But what is interesting in this graph is that when we used a mix of mussel and feed, the growth performance, so let's say the final body weight was higher than in the 100% groups, both when we used only feed and only mussels. This can be something interesting to talk about, of course. Our idea, of course, my idea in particular is that when we mix 2 different ingredients, we provide to the fish a wider array of nutrients, okay? And this, of course, can be useful to promote the growth. I'm thinking mainly to essential fatty acids or essential amino acids. Of course, the feed are more balanced than normal, than only mussels, so only feed showed a higher performance than only mussels, of course. When we went to check other parameters, the technical parameters such as feed conversion rate, cioè, better say, the ability to convert feed into meat, okay, we observed that those mixed groups where we provided the muscle and feed, we got the best conversion, notably for 60% feed, 40% muscle. Similarly, we observed these characteristic trends about the hepatosomatic index, which is, how can I say, specular. I mean, the trend is similar to those observed for growth, but when we get better growth, we had less incidence of liver on the body mass. This means probably that the metabolism of liver is improved when we provide a more balanced diet. And this is what we saw when we mixed the two raw material. To be short, I want to show you also other results, and then let the time maybe for questions, if you have questions. These are the results of the second trial, because based on the fact that when you mix raw materials, ingredients, to make a more balanced diet, you get better growth. In this case, we mixed the muscles, as we saw in the experiment 1, together with the clams. The diet was composed by 50% muscle and 50% clams. In this case, we just made two groups with replicates. So each group was replicated 3 times with the 3 replicates. And the body weight was initial body weight again of Sibrim was 6.8. And the trial lasted 7 weeks. Again, in this table we have the overview of the results of the data, but probably using the graph you can get a good idea. And we saw that the final body weight again was higher for the group fed only feed against the group fed only muscles. So this is a confirmation of what we saw in the trial, in the experiment 1. Even also the length was affected, okay, but of course the length is strictly correlated with the body weight. So higher body weight very often is very comes together with the higher length of the fish. But what is important, it's confirmed, all these data are confirmed by the SGR, which represent the ratio, the daily growth ratio, okay, how much the fish grow per day. And again, the group fed only feed growth grew better than the fish fed only muscles. FCR, this is inverted, okay? This is the group with feed, 100% feed, and this is 100% muscle. So this group showed a better increment, better conversion of the feed into product, into meat, fish meat. Aqua feed perform better than all mussels and clams together, okay? Hepatosomatic index, it was again better for, sorry, in these 3 graphs, they are inverted in comparison to the first 3. I didn't realize this. I just realized now. Anyway, feed showed a lower hepatosomatic index and higher viscerosomatic index. This means that probably the fish fed only feed has more deposit, fat deposit at abdominal level. So it's new that fish fed aqua feed are more fatty than wild fish, and this is something that confirms this trend even in our conditions. Experiment 3, we added to our diet one more ingredient, mussels, clams, as we saw in the experiment 2, plus polychaetes. The ratio was 50% mussels, 30% clams, 20% polychaetes. Even in this case, we performed just 2 groups with the 3 replicates, in which one group was fed only aqua feed, commercial feed, and one group only our mixture. This trial is still ongoing. We are still collecting data and feeding this fish with this diet. So we expect the final data. By the way, we are already at 6 week, let's say. This is still already hold 6 week trial. So we are close to the end. We already got 80 grams as a final body weight for the group fed only feed. You can see we started from 37 grams, so we already duplicated the initial body weight. And still the fish fed only feed grow better than the fish fed the mixture. Okay. Similar results also can be seen for the other parameters, and again I show you the graphs to better understand what's going on. As you can see, feed conversion rate is one of the most representative parameter, because it's the sign of how the diet is converted into products, and feed still converts better than the mixture, the experimental diets, let's say. Okay, so I can come to the conclusion, so I can leave some time for questions if you have some. But before, I want to make some. I made some. Me. Yes, okay, but how much it costs? How much does it cost if we do this? Because it's important. It's easy to get good results if you spend too much money. So we have to know how much it costs. So I made some very simple calculation. So I realized that then we use these experimental diets, fresh diets, let's say, with the mussel, polychaetes, and clams. Approximately, we observed a loss of production of 11%, which, considering the price of the sea bream in the market, okay, I mean the price for producers, which is 80 euro per kilo, this production, the loss of production, means 880 euro per ton of fish produced. Okay, just to have an idea. So we are losing money if we are going to feed the fish with this system. By the way, these questions, it's really important. Okay, that's true. We are losing some production and then money, but what we are getting probably sustainability. So may this 880 euro per ton the price we pay in order to improve aquaculture sustainability? This is a question that, I mean, governments have to respond, have to decide if it's better to produce less to increase aquaculture sustainability, the food chain sustainability. then we have to also consider that with this production, correlated to this production, there will be another kind of production, which is the crop production. We have to consider. We are losing this 11%, but at the same time, with the same energy, we are going to produce even crop. So probably if we make a total balance of the system, the SIMTAP as well as other kind of aquaponic system may be really interesting even under the economical perspective. But anyway, if we really don't want to lose this kind of production of money, let's say, we can think and study better, of course, the idea to partially replace the feed. In our first experiment, we saw that when we replaced the aqua feed at 40%, so we provide 40% muscle and 60% feed, we got 9.7% more production compared to the use of only feed. More production. So partially replacing the feed may be economically convenient. And this is the amount per ton of fish produced. So in this case, we earn 776 euro per ton if we partially replace the feed. Of course, this data must be confirmed, okay? Other studies have to be carried out, led, and for example, we can work on our experimental diets to improve its efficacy by including new raw materials, so not only mussels, clams, and polygates, but why not holoturia or shrimps, let's say. And at the same time, we can also think to add some mineral or vitamins that may lack in this kind of experimental diet. Okay, so this is something to work on for the future. Okay, so this is what we can start to do when we will be working with the CBAS in the next trials that are coming in the next days. Some results of our work. We already made 2 publications, one on the aquaculture, which was about the methodology, the choice of the species to be more suitable for SIMTAP production. And these results I show you, we are already going to present this data more deeply, more comprehensively in the next European Aquaculture Society, Aquaculture Europe 21, that will be held in Madeira on next October. So we will have an oral presentation at that Congress. Thank you for your kind attention, and I would like also to thank Mr. Lorenzo Rossi, our PhD student, which is very, very effective and very helpful in all our works. Thank you so much.
Thank you, Baldo.
I have a question.
Okay, please.
Thank you, Baldessara, for sharing results with us. Maybe I missed a detail about the presentation of mixture of muscle duplicates. How did you give those dyes to fish?
Just fresh chopped. Okay. In practice, in this stage, the preliminary stage, we are not producing the mussels, polygates. We are producing mussel and polygates in our SIMTAP, but we have no large production in this moment. So we use the frozen mussel and clams and polygates. But we didn't process at all this product. We just thawed this kind of product. We chopped according to the fish size when we were working with the small fish, juveniles, 5 grams juveniles we chopped with to make smaller particle size. Now we are working with the 80 grams seedling, so we are chopped with the larger particle size, but we don't process at all the products, mussel, polychaetes, and whatever. And what I can tell you is that for sure this kind of diet is more appreciated by the fish. They really like this diet, and they compete extremely dramatically compete to get food because they really appreciate this kind of products, diets.
Okay, thank you, Baldo.
You're welcome.
Thank you.
You're welcome.
Now is the time for, in principle, Joel or Bean. Okay, thank you.
Good afternoon, everybody. My name is Joël Aubin. I am researcher at INRAE, and I will present you the interaction of aquatic species in coastal pond IMTA, a case study in Charente in France. The partnership of this project linked two teams. One from INRAE, which is the National Research Institute for Agriculture, Environment and Food, and specifically our research unit, which is specialist in environmental assessment and design for agri and aquaculture systems. And the Lycée de la Mer and du Littoral, which is based in Charente, which is a general and technological school, which has also professional license with La Rochelle University, an oyster educational farm, and educational aquaculture facilities. The rationale of the prototype I will present you today is based on the different risks. Despite the increasing demand in seafood, there are several factors which impair the development of aquaculture in Mediterranean countries. Specifically, the global changes, such as climate change with an increasing frequency of warm periods, the price volatility of seafood and the inputs, especially for aquafeed, the availability of resources in competition with human or livestock. There is also the environmental impacts, such as the emission of pollutant in the surrounding aquatic ecosystems, the settlement of the activity on sensitive areas, such as coastal areas having specific biodiversity, the use of fragile resources, such as fish meal and fish oil, and the contribution to climate change. There is also the perception by consumer and citizen, which question us, as the consumer can consider aquaculture product as another kind of intensive livestock product. There is also the comparison with fishery, which are considered more natural resources than aquaculture, and the competition for access to coastal areas, especially with tourism. The prototype that we built is based also on different principles that were predicted in a previous study, which could help to drive the development of agroecological pond systems. The idea is that the system that we want to promote should be productive, robust and resilient, having natural and cultural values, being environmentally friendly, using local and natural resources. And all of this principle lead us to think that integrated multi-trophic aquaculture can be a solution. Integrated multi-trophic aquaculture is generally designed in this way. You give feed to fish, which emitted in the environment dissolved minerals, dissolved organic matter, and particulate organic matter, which will support the development of primary producers, secondary producers, filter feeders, and deposit feeders. In all of these species, we concentrate our study on algae, mollusks, and crustaceans. Therefore, the prototype we propose is productive because we chose to produce species at good yields, having good yields and having economic sense, such as oyster, clam, prawn, sea bream, and ulva. It should be robust and resilient, as we produce several species to balance market variations, and because we chose robust species adapted to fluctuating environment. It has also cultural and natural value as it uses species which have gastronomic values, which are recognized by the people in the country, and they are really in traditional oyster pond that are inserted in the local landscape. It should be also environmentally friendly, as the system is based on the recycling of the nutrient, and it closes also the water loop, and it uses a low level of energy. And finally, it uses local and natural resources, as we chose to make a particular feeding process to date, as we used only low level of feed with no fish meal and fish oil and with no imported ingredient, and complemented with local discarded mussels. Before running the SIMTAP prototype, we wanted to check if it was possible to feed sea bream without fish meal and fish oil, using only vegetable feed with mussel complementation. Therefore, we built a small experiment based on young sea breams of 7 grams, spread out in 3 groups, fed with commercial feed 6 days a week, vegetable feed 6 days a week, or with the vegetable feed during 5 days a week, and mussel added at isoenergetic level. What we observed is that the vegetable feed induced a lower growth than the control, but the addition of mussel permitted to reach the performance of growth of the control. Nevertheless, there is a large decrease in polyunsaturated fatty acid composition of the flesh, especially for the vegetable fed sea breams, with a little increase when we use mussels. The prototype was based on the closed loop of 4 ponds. The first pond received the sea bream, which were fed with formulated feed without fish meal and fish oil, added with fresh mussels out of calibration 1 day a week. The water from this pond goes to a second one, where shrimp and oyster grow. From this one, the water is sent to a third pond where oyster and shrimp grow, and at the end, the water is sent to a fourth pond where there were clam and shrimp. From this fourth pond, the water is sent back to the sea bream pond. Water inflow was only used at high tide to renew a small part of the water, and the water in surplus was sent to the ulva pond. Air blower was settled in each fish or shrimp pond. The growing period was from May to October 2020. During the experiment, we made also control of the quality of the water. Here you have, as an example, the oxygen saturation on control of a 24-hour cycle. You can see that in July we had variation between the daylight and the night, with sometimes for some of the ponds very low levels of oxygen. In August we had very high variation inside the ponds, especially with oversaturation of oxygen due to due to the phytoplankton concentration. And you see that there are many differences, high differences between the ponds. We made also control on phytoplankton concentration at 4 days, and you see that there is an evolution of the concentration from June to October with a high level of brown and green algae concentration in the reared pond. We will now show you some of the results. First, about the growth of the gillhead sea bream. We had good results of this, except on the first period due to the adaptation of the fish in the system. You have to know that these fish were reared previously in a RAS system with high water quality. But the growth overall was good, and they reached the weight that was expected. The feed conversion ratio in equivalent equivalent formulated feed was around 1.9. That was expected also, and the survival rate was around 90%. We observed the same resultant in the preliminary experiment, that the total polyunsaturated fatty acid were decreased. Considering the prawn, we had mean weight, which increased 9-fold. That was as it was expected. There is also a high variability of weight due to the sexual dimorphism in this species. Unfortunately, all the prawns from the pond number 6 died just a few days before harvesting due to unexpected climate event. So therefore, but the survival rate around 38% in pond number 5 and 58% pond number 4 was considered as correct. So good growth and correct survival rate, except for the pond which supports the climate event. When we look at the oysters, we obtain a good growth and a good survival rate estimated at around 90%. It was unexpected because in this area we observe summer mortality for oysters, and here we didn't observe this. So it was a very good result, and the fill rate was over the quality standard, which was 12 to 15%. This is the quality standard, and here we reached the flesh yield was around 20%, which was very high. So a very high quality product with a very good survival rate. And when we look at the clam, we observe also a mean fill rate over around 20% here, which was a good increase from the one we stocked at the beginning, and the survival rate estimated around 70%, with a very good growth as expected in this production area. For the ulva, the results were not so good, as there were no production of ulva due to lack of water movement, and we want to test this anew with a change in the water loop. To sum up, we can see that we had good results for sea breams in terms of growth and survival rate. We had very good growth and quality for oyster and shrimp in the pond number 6, up to this climate event where all the shrimp died. We also had very good results in terms of quality and growth of shrimp and oyster in the pond number 5, and the same for the clam and shrimp in pond number 4. But for ulva, I think it failed, so we have to think anew about the design of the system. So If we look at the principle that we dictated at the beginning for the production, yes, it was not so bad about the productivity, the best for the oysters, and we had good results for clams and shrimp. And we have to reconceive the system for the algae production. About robustness and resilience, yes, it was the case for oysters, but as you see, it has to be consolidated for fish and shrimp. For the natural and cultural value, we made samples for a biodiversity diagnostic that is in progress actually. And considering environmentally friendly, there were almost no emission of water during the production, and there were very low level of nutrient emitted in water. And for sure, we used the local and natural resources with the good performance of the sea bream using the vegetable and the mussel feed. As perspective of this work, okay, we try again, as we have a new run of the system in progress actually, to confirm the result we obtained last year, with several changes, such as the probes that will be settled to have for a close monitoring of the water quality in several parameters, such as pH, oxygen, temperature, etc. Revision of the air adduction and the water loop to avoid the death of the shrimp we observed last year. A better management of the ulva production. The pond of the ulva is now in the water loop. And we mixed oyster and clams in the pond with shrimps to obtain a better use of phytoplankton. We'll see that. In parallel, we are building a model, a dynamic modeling of the growth of the different species and the fate of the nutrients in the system. And we start to make dissemination to local producers, students, and scientists. Thank you for your attention, and don't hesitate to contact us if you want some more explanation. Thank you very much.
Oh, nice presentation. Unfortunately, Joel is not here. I don't think there is a possibility to ask a question to Joel, but Joel provide the email, so you can contact him for any question about the work they are doing in France. So now is the time to give the floor to Dr. Mehmet Koser in Turkey.
Hello everyone.
Thank you.
Hello everybody. I will continue instead of my colleague Mehmet Ali with my presentation. My presentation will about SIMTAP prototype testing. This prototype is the pilot production place that we built in Medfree. And also I will focus on nutritional value of polychaete for European sea bass and sea bream. Here you see the contents of my presentation. I will give a brief information about our aim, and also I will show you some of our results in terms of SIMTAP prototypes assessments for the fish performance in terms of growth and feed conversion ratio. And also I will share some results from 2 experiments that we conducted on European sea bass and gilted sea bream. And also I will finish my presentation with a conclusion slide. You will see the aims of our studies here. First of all, in the test of SIMTAP prototype, in terms of growth performance, we aim to see the possible weak points in the system, evaluate the resilience of the system in case accidents such as oxygen drops, power failures, filter breakdowns, etc. And also we would like to compare it with the flow-through system in terms of growth performance of fish. Other aims from the studies that we conducted here. Briefly, I can say that SIMTAP aims to utilize particulate fish waste as feed for growing polychaetes, at least in our system, then use of polychaete as feed or supplemental feed for fish in the system. So before use of polychaete as feed for fish, its nutritional evaluation is required in the target species, which are European sea bass and gilted sea bream in our case. The study is aimed to fill the information gap in terms of nutritional value of polychaete. Of course, Baldessara conducted very good experiments, and then he gave us very good information and explanation in terms of the nutritional value of polychaetes as well as other animals, including mussel. Let's move to main results. In test of a SIMTAP prototype, we used 2 fish, European sea bass and gilted sea bream, and then we stocked those fish, 2 replicated tanks. The tank volume was 5 tons, and the experimental systems were 2. One of these is a flow-through system, the another is SIMTAP prototype system. Duration of experiment was 150 days for control fish and 151 days in SIMTAP system. We had an accident in the SIMTAP system, so we restocked the fish. I will tell you later about the details. And then we used the commercial diets in this test. For starting from 2 millimeters to 5 millimeters in diameter. Feeding level, daily feeding level, I mean, was set at a bioenergetic model, and then we gave the feed twice a day. And the main responses in the test was growth and feed utilization. Here you see the 2 systems, the details. And then in the left-hand side, you see the flow-through control units consisting of 4 tanks, 2 for European sea bass, 2 for gilted sea bream. And the right side, you see our tanks in the SIMTAP systems. And then you see 4 tanks with 5 tons water volume. And we allocated fish to 2 tanks per fish species. In this graph, you see the mean growth weight of fish, European sea bass in the control unit and the SIMTAP system. You see some fluctuation during the experiments in the growth, and at the end of the experiments, we didn't see any significant differences between the 2 systems in terms of growth performance of European sea bass. In this graph, you see the growth of sea bream. You see some significant differences between the system in terms of growth of sea bream, and but these significant differences coming from another reason, not from the system itself. I will give you some details in the next slides. And you see, after starting the experiments, we had a power cut in the SIMTAP system, so we had to restock fish to the system. So we started the SIMTAP system a little bit late compared with the control group. You see, the duration difference is only 12 days. In this point or on these dates, we reduced the stock of fish in the system by reducing the number of fish. In case of European sea bass, we reduced the fish stock twice during the experiments. And in European sea bass, the European sea bream species, in SIMTAP system, we reduced fish stock only once, compared with the twice that were in the control system. In these graphs, you see the change of fish stocking densities by the dates. We started almost 5 kilogram per cubic meter for European sea bass, and then it increased almost 20 kilos per cubic meter towards the end of the day, but we reduced the stocking density in the last sampling, and then the stocking density decreased about 10 kilo per cubic meter. In terms of European sea bream, during the restocking of fish in the SIMTAP system, we used a little bit less fish compared with the control system. Therefore, our stocking densities were a little bit lower than the control. Therefore, fish were able to grow better than in the control system. Therefore, our fish that you saw the performance in the previous graph showed better growth compared with the control. But here, interestingly, in both systems, the stocking densities reach over 20 kilos per cubic meter, meaning that our SIMTAP system is can provide very good condition for fish growth. The rows indicate the dates that we reduced the fish stocking densities. In this slide, you see the feed conversion ratios of the fish species kept in both systems. We didn't see any significant differences between the species and also systems in terms of feed conversion ratio. Let's move to a feed experiment that we conducted on gilted sea bream. Before moving, I will give some details about the supply of polycate material, because it is so difficult to collect enough material to conduct the experiments. Actually, we provided polycate from Aegean Sea region of Turkey with different batches, and some batches arrived as frozen, as you see in the picture. Also, some batches arrived as live, kept around the urva leaves, and then we separated and cleaned them, and then we dried using 2 methods. If the batch arrived as in frozen, we dried it using a freeze dryer, as you see in the picture. And if they arrived as live, we moved them to frozen, and then we dried them at the oven at mild temperature, 65 Celsius degree for overnight. And on the right side, you see the 2 materials, powdered materials, from freeze-dried and also oven-dried. But in the experiments of European sea bass and gilted sea bream, we had to mix both material before including to diets, because the materials are very low in amount. So we had to combine them instead of using them separately. I would like to give some information about nutritional composition of polycate in comparison with the fish meal that we used in the experiments. Fish meal composition belongs to a mixture of fish meals, actually. from 3 different sources, and their protein is very high, as you can see. Polycate material has a less amount of protein compared with fish meal, and lipid level is comparable. Ash level is also comparable. We actually analyzed their fat acid composition, but the results arrived me just so that I couldn't make any evaluation for that. Let's talk about condition of experiments. Replication is 3. When we tried polycate material in 5 groups, starting from 0 in the control, we included in the diets up to 20% of the diets. And tank volume was 500 liters in the experimental system, and the experimental system was running through flow-through systems. Next, in CBAS experiments, we used fish with the initial weight of 15 grams. We had to stock 10 fish per tank because feed material was very low, so we had to reduce the fish number as much as possible. We adapted to fish for weeks for the experiments. The duration of experiments was 53 days for CBAS experiments. Pellet diameter was 2 millimeter. We fed the fish ad libitum twice daily. And then you see the variables that we checked in the experiments. And then you see some pictures in the, that we taken during the diet preparation, and then some more pictures from our experimental system, and then the initial whole body sampling. And you see in this table about our experimental formulation of experimental dyes and their nutritional composition. You see we included polycate meal up to 20% of diets instead of fish meal, and we also reduced some fish oil. Not so much, but only 0.5%. And we also included chromic oxide as inert indicator to estimate the nutritional digestibilities. And then we set protein and lipid at 50% and 40% respectively. You see the you see the growth of fish at the end of the experiments, and then we didn't see any significant differences between the groups. In this slide, you see the apparent nutrient digestibility coefficients of diets, and as you see from the graph, there was a significant linear increase in dry matter digestibility, protein digestibility, energy digestibility, and organic matter digestibility with the increase of polycate meal in the diet, meaning that inclusion of polycates in the diet instead of fish meal has a positive effects of several nutrient digestibilities. I swapped the pictures. I am sorry. It should be gilsisibrim, not CBAS. Yeah, let's move to experimental condition. Experimental conditions were the same with the European CBAS experiments, except fish weight, as you see, and also duration of experiments. We terminated it 2 days later. And you also see the formulation of experimental diets in this table, also the inclusion levels of polycate meal. And we set the protein and lipid a little bit lower compared with CBAS, as you can see from the table. In this graph, you see the growth trajectories of fish fed on different levels of polycate meals. As it was in the CBAS, we didn't see any significant differences between the treatments in terms of fish growth. In this slide, you see the apparent digestibility of nutrients, and we saw a significant linear increase in dry matter digestibility with the polychaete inclusion level. And also we saw the similar tendencies, not significant, but we can say significant tendencies, a linear increase with the polychaete meals in diets in lipid, protein, energy, and organic matter digestibilities. In this slide, you see the fish in, fish out ratio of sea bass and sea bream fed varying levels of polychaete meals in the diets. And you see there is a linear increase in both species in terms of fish in, fish out ratio with the increase of polychaete meals in diets. And also the ratio dropped below 1, which is very nice actually, when the polychaete meal was included at 20% into the diets in both species. Let's make a general conclusion. We can say SIMTAP prototype in Turkey can support high stocking densities and good growth conditions for both species. And another general conclusion is polychaete is a valuable feed ingredient, which is equivalent or better in some aspects than fish meal for European sea bass and sea bream. That's all from our side. Thank you for listening to me.
Thank you very much, Hussein. Interesting results. I think that Daniele was able to manage the presentation by Mehmet. Mehmet, are you online now?
Okay. As the fastest growing food producing sector in the world during about half century, it was projected that major contribution to seafood supply will provide by aquaculture during the next future. While the pressure on environment is getting increased day by day, the multi-trophic aquaculture may get a solution for aquaculture environmental impacts. Moreover, under the conditions on increasing difficulties access to limited resources, such as raw materials of fish feed, a self-sufficient multi-trophic production system is a new concept that may provide an assurance for sustainable fish and crop production. When the revival aquaculture is kept aside, marine aquaculture in Europe and the Mediterranean is dominantly carried out in cage culture. For example, marine aquaculture in Turkey, which is one of the leading actors for aquaculture originated finfish supply of Europe, is mainly based on cage culture of European sea bass and gilthead sea bream. In 19, production of these two species represented about 2 types of total production. In Turkey, a total of 404 farms are actually in progress. Although there are a few earthen ponds, in marine finfish farms are mainly of cold cages. Juveniles of European sea bass and gilthead sea bream are supplied from 27 on-land hatcheries located mainly Aegean seashores. These marine finfish hatcheries are flow-through systems which they use brackish surface and groundwater. Sustainability of marine hatcheries was the major source of inspiration for the SIMTAP concept in Turkey. In fact, marine cages have been faced to many of environmental restrictions during the beginning of this century. For the last few years, marine hatcheries are fixing governmental authorities' attention due to eutrophication and pollution risks of brackish surface and coastal area, as well as groundwater salinization results from withdrawal. It is an expectation that capacity restrictions or installation of recirculating systems will be forced to marine hatcheries in a short-term period. In this context, the SIMTAP concept in Turkey mainly aimed to test a cost-effective recirculating aquaculture system for SIMTAP prototype under extreme environmental, and to test a SIMTAP prototype as an alternative for traditional on-land marine hatcheries, and to test a possibility of economically sustainable use for what were the components of the SIMTAP prototype installed in Turkey? The system mainly was consisted of 5 compartments covering fish culture unit, RAS equipment, polychaete unit, hydroponic unit, and microalgae culture unit. I will try to shortly describe the system with a diagrammatic representation. The system is fed by full-strength seawater with a salinity about 40 per thousand from the eastern Mediterranean Sea. The seawater was first filtered through a particle filter and then disinfected by UV irradiation, followed by ozone injection. The filtered and disinfected seawater is pumped into fish tanks through a second UV disinfection system and degassing column. Fish rearing units consist of 4 round tanks with a capacity of 5 cubic meters. The flow out fish tanks is directly piped by gravity into the 2 modified radial flow settlers. Solids were manually flushed once a day before from the bottom of settlers. Top flow of radial flow settlers was gravitationally discharged to a settling tank, which has manual cleaning filters. Our flow of effluent was drained to biofilter, was drained to a settling tank, and then a protein skimmer, and then a moving bed bioreactor. The system was aimed at simulation of a small commercial model of about 400 square meters area. Therefore, capacity of the compartments was installed at a commercial scale. You can see some parts of compartments of the system in the slide. Although the system installation has completed at the end of March 2020, unfortunately the work stopped due to pandemic conditions. Therefore, test of system was able to start end of May 2020. The fingering about 1 gram in early growth stage was not supplied due to the breeding period of hatcheries. The other compartments of the SIMTAP concept, including halophyte and polychaetes, were not integrated due to the lost spring period. Therefore, the test on the prototype was started on June 2020. hydraulic connectivity and flow rates between the compartments were balanced during this period. Under these conditions, a few studies were completed, which a study on stem startup and biofilter condition is one of them. A commercial scale, a commercial mixture of bacterial cultures was inoculated in a moving bioreactor. Ammonia as media was supplied by ammonium chloride addition. European sea bass and gilthead sea bream were stocked at a density of about 7 kilogram per cubic meters and 9 kilogram per cubic meters on the 79th day of the experiment. Moving bioreactors were monitored daily or every other day for a total 123 days. Acclimation of ammonia oxide you can see the figures that acclimation of ammonia oxide oxidizing bacteria was recorded on 40th day when a sharp decrease in ammonia and a sharp increase in nitrate. Acclimation of nitrate oxidizing bacteria was recorded when a sharp decrease in nitrate on 9th day. Nitrate also showed a sharp increase in trend during the 9th day. The results indicated that the complete acclimatization of nitrifying bacteria nearly took 3 months in the SIMTAP prototype built in the Eastern Mediterranean under high temperature and high salinity conditions. Volumetric total ammonia conversion rate changed between 0.1 and about 33 gram nitrogen per cubic meters per day during start and acclimation period. And volumetric total ammonia conversion rate highly dependent on ammonia is well known, highly dependent on ammonia and dissolved oxygen concentrations, and is limited by low ammonia or low dissolved oxygen concentrations. So we revealed that in tested SIMTAP prototype, a relatively low nitrification rates due to low ammonia concentrations during a short period of system startup with immature biofilms. Another task for us assessing polychaetes, breeding conditions, and nutrition. Last year, we conducted some experiments, mainly based on experience, but a complete integration of polychaete units to SIMTAP system could not be achieved yet during the first year. Now, recently, polychaete specimens Nereis diversicolor or Hedis diversicolor have recently stocked into tanks of SIMTAP system with a density of 100 individuals per square meter. Experiments on microalgae culture during the last year, a growth observation of Nanochloropsis oculata was tested indoor conditions because the high temperature during the end of the spring and beginning of the autumn in Antalya, about 40 degrees centigrade in indoor conditions. Therefore, we will conduct studies during only autumn, between autumn and spring. Experiments on microalgae culture covering the batch culture and as possible a continuous culture of Nanochloropsis oculata, Hydrochrysis galvana, and Dumariella salina in polyethylene bags will be conducted between next autumn and another experiment, not experiment, really is a monitoring period related to water and nutrient balance modeling in SIMTAP prototype. During the first experiment period in 2020, we cannot monitor to continuously. Therefore, we cannot produce any mass balance mass flux in the system. But we will monitor the system during this month. During 8 months, actually, next 8 months. Therefore, we will calculate the water and nutrients mass flux between the SIMTAP compartments, and I hope we will this part of the study maybe harder part for us. I hope we will complete the study on water and nutrient balance modeling up to 8 months, 9 months. I hope. Another task is fish early stage growth determination of growth performance during fish early growth stage. Actually, this study, the experiment was started at June 10th by using same fish tanks and stocking density. A flow-through system was using as a control. European sea bass and Gilhead sea bream were stocked at a density of 3 per cubic meters respectively. Fish are fed at predetermined levels based on total biomass in each tank 6 times a day. The experiment will be conducted about 2 months, and after the experiment, the system will continue to grow out period of the for the sea bass and sea bream during 8 months. the fish early growth stage experiment will be repeated on March next year to test the growth in cold water temperature conditions. Following the experiment of ongoing fish early stage growth experiments, the system will be continued with second experiment of growth period up to market size. During this period, the water and nutrient flux will be determined. For the next period, for about 1 year, some tests will also accomplish it. The last word, the main target in the next period, the integration of the SIMTAP compartments, achievement of continuous production of fish, halophytes, polychaetes, and macroalgae, determination of nutrient flux in the system, improvement of the system performance, and diversification of the species captured. Thank you for your attention, and sorry for this situation.
Thank you, Mehmet. Thank you. We are a little bit late, but not so much. Daniele can start with his presentation about the monitoring and control system for the prototypes installed in different countries. Please, Daniele, go on.
Thank you very much, Alberto, and thank you to everybody listening. Yes, so we are going to talk about the smart monitoring and control system for the SIMTAP pilots and energy efficiency and the definition of the best places where SIMTAP plants can be installed. First of all, I would like to say that unfortunately my colleague Alberto Barbaresi is not able to be here with us. He was supposed to present part of the presentation, but let's say he is not here with me because as Joel was saying before, we are now covering with our monitoring system also the SIMTAP pilot in France, and Alberto is, while we are talking, is taking care of our monitoring system in France right now. So basically, let me first of all very shortly welcome you to the University of Bologna, which is considered the oldest university in the Western world and the first university in Italy based on the QS World University Rankings, with more or less 3,000 professors and researchers and 3,000 technical staff, more than 30 departments, and more or less 90,000 students. We have a high number of European projects from the Horizon frameworks and of course other frameworks including PRIMA projects, more than 400 European projects attracted over the last years. Our group is the Department of Agriculture and Food Sciences, which is a leading institution in the agri-food system, covering basically all the scientific fields in the agricultural production, food processing, and livestock production fields. We are an excellence department of the university ministry in Italy, and we are also ranked in the top 50 ranking of QS. This is our research team. So we are a very interdisciplinary research team, our agriculture and biosystems engineering group, and in particular our group is the structures and environment group. We basically deal with the design and modeling and monitoring of smart agri-food structures and systems, with smart farming and precision livestock farming, with energy modeling and the renewable energy in the agri-food and livestock systems, and with the multi-criterial and suitability analysis in a GIS environment, as well as with big data and rural planning. And we are really excited that probably we needed a project like the SIMTAP project to, let's say, bring together different activities and different fields of activity, because basically the SIMTAP project is covering almost all these fields, which usually are, let's say, dedicated to specific research projects. So SIMTAP is really a cross-sectoral and cross-disciplinary research project. In this project, we mainly take care of three tasks. The first one is the realization of a smart monitoring and control system. We have called it ISMAX, specifically designed for the SIMTAP prototypes. We will start from that. Then we also have to manage the energy efficiency assessment and optimization, as well as the definition of the optimal places where the SIMTAP plants could be installed in the Mediterranean region. So let's start from the smart monitoring and control. Why smart monitoring and control applied to such an innovative and, let's say, visionary system? In general terms, we could say that ICT and IoT can bring many benefits in the agri-food sector. For sure, they can help an efficient management of agriculture and livestock systems. They can improve food safety and traceability, and also they can improve sustainability and animal welfare, and for sure can provide objective data and, let's say, quantitative data about the sustainability and efficiency of these systems, of the agri-food systems, as well as providing data and information for monitoring animal welfare. We are talking about fish in this case. We are not that familiar for now in talking about animal welfare applied to fish, but for sure animal welfare will become more and more important also in the fish rearing sector. Of course, we know that all these things have a huge impact on the market, also due to the increased awareness of consumers. So being able to provide objective data about sustainability, animal welfare is increasingly important. SIMTAP systems are prototypes with a very advanced and visionary concept of integrating different trophic systems and levels in a unique system. Therefore, SIMTAP systems need for a very precise and delicate balance among different modules of the system, as well as their various species and the surrounding environment. As you have seen in the previous presentations, the SIMTAP pilots work in very different environmental conditions and with different production cycles. So this, let's say, challenging context calls for a continuous and precise monitoring of different metrics. This system must be flexible, scalable, and open. Moreover, we need an integrated system, which means integrated within each plant. So in each pilot plant, we need an integration in monitoring across different matrices and domains, which means air, water, and energy, and also among different SIMTAP plants throughout the Mediterranean region, so in different countries. This means that no available solution on the market was suitable for the specific needs of this research project. Therefore, we have designed and developed in our lab an integrated smart monitoring and control system. Our system is able to monitor all the environmental data, which means weather data outside, water and air data inside. You've seen that, for example, in Pisa and in Turkey, we have closed environments or protected environments, while, for example, in France, we have an open pond situation. So when we talk about indoor or outdoor situations may be different from one pilot to another, but we are able to cover both indoor and outdoor monitoring across different matrices, so water and air. This system can both create a database with the time series of the collected data, so let's say increasing volumes of data. At the same time, the system can allow a real-time remote control of data, thus allowing to increase the operation precision. Basically, the system has been designed to trace conditions where animals, fish, and crops grow. So we can trace back to analyze the conditions where fish and crops have been grown and will grow. We can optimize human operations. We can increase the reliability of the system, for example, providing real-time alerts in case of system failures. We can also provide data for research, which is another important task and goal, because we don't only need to monitor in real time the conditions, but also to store data to support the analysis of the performance of production. Of course, performance of production can change if environmental conditions change. We can support the analysis of energy efficiency and also the sustainability assessment. And we have a, let's say, double scope of the system, because basically during the project, so during the 3 years duration of the project, the monitoring system will allow to develop and test the system itself. So it supports the trials of the project. At the same time, it can be a very important part for future commercial exploitations and applications of the system of each part by itself. So we have gone through the research, design, prototype, development, and validation of the system. Basically, we have analyzed the specific characteristics of each experimental site, and we have found the most suitable sensors and sensor networks. Honestly, we have designed the sensor networks from the scratch to analyze the different environments. So basically, our system measures and monitors the main parameters in water, dissolved oxygen, pH, and electric conductivity. The main parameters in the air, which means temperature, relative humidity, carbon dioxide, and photosynthetic active radiance, so light, basically. The external conditions, temperature, humidity, air pressure, air, wind, velocity, and direction, and light again, and also energy consumption. Our system must be capable of resist in different and also severe environmental conditions, must be energy efficient, which means also being able to produce energy and be self-sufficient in energetic terms, and flexible and scalable. You can't see a complete list of water quality parameters, for example, here, but our system is ready to implement additional water quality parameters. I will not go pretty much into the details, but basically the system consists of a node which is collecting data from different sensors. The good thing is that we only have one node and one gateway which can collect data from different sensors. Which means if we add a tank, if we add a pond, the system is completely scalable, flexible, and can be easily implemented. Then the gateway is connected to internet. We have a server hosting the data here at our university. We also have a redundant system with everything stored also in a remote geographic position in a cloud. And this is connected to the applications from each partner. Basically, each sensor is harvesting energy from the sun, which means that it can back up in case of energy grid failures, and it can be, let's say, virtually independent from the grid for long periods. The system can store but also process data. And we have developed an interface, which is a double interface, basically. So we can receive data from the sensors, but we can also provide feedbacks and, let's say, activate processes through actuators. So the system is really suitable to both monitor and control. Now we have the system running in Italy and in Pisa and in France at the Lycée de la Mer et de la Littorelle, but we are ready to cover also the other pilots. You are now seeing a few pictures of our prototypes in Pisa. In this case, we measure the external conditions, temperature and humidity within the greenhouse, temperature, pH, electrical conductivity and dissolved oxygen in the water where the fish grow, and also photosynthetically active radiation, which means light inside the greenhouse. So this was our very first pilot where we started testing the system and collecting data. It's completely operational at the moment, and it's providing data for operation and for further analysis. These pictures come more or less live from France. So these are, I guess it's the very first time that Alberto is seeing these pictures also. So basically, it's the system that is now running in France. It's completely different, of course, because as you have seen from Joel's presentation, the system in France, the SIMTAP in France is a completely open pond system. So we had developed a flexible system able to, let's say, work off-grid, both for electricity and internet, and it's able to provide real-time data, as Joel was explaining, in each pond to control the system. So how we can handle the data? Basically, we can handle data in real time or backwards. We have developed a user-friendly interface to see and analyze data about different parameters. As you can see here, this is about wind, for example, humidity, light, and pH in the water. So a real-time interface allows us to both see real-time data and also time series. And of course, we can also download big data amounts to perform our analysis. We have started the next, let's say, the next steps of the research. Of course, this monitoring system called for validation and calibration because we had to perform a very sound validation and calibration for all the sensors, as you can see here. We have started the energy efficiency analysis for the Italian pilot in Pisa. Basically, we have started analyzing the data about energy consumption. As Carlo was saying before, the pilot in Italy is also aiming at analyzing very severe and extreme conditions, for example, in summer, which means that air temperature must be kept under control. So we are measuring energy consumptions for pumping water, for controlling temperature in summer and for heating in winter. And we are analyzing energy consumption, energy needs in relation to external and internal conditions, water and air conditions. So we are trying to define the most, let's say, energy demanding steps and periods and processes, and this will be the basis for let's say analyzing how we can improve the energy efficiency of this pilot. Of course, sustainability is probably the key point at the basis of the SIMTAP project. So we want to take care also of analyzing the energy efficiency and to find a way to improve further the energy efficiency. So in the next months, we will address the study of how to improve energy efficiency, which will become an important point for future installations. And last slide, we have also started the analysis of the optimal locations where SIMTAP pilots could be installed, which means which are the best places where the SIMTAP pilots can use the environmental resources in the best way possible, and let's say also find the most favorable conditions to be efficient in terms of production and low environmental impact. So we will perform a multi-criteria spatial analysis in a GIS environment. We will start georeferencing data about fish farming, about aquaponic companies and other agricultural activities, in particular greenhouses, because runoff water from greenhouses can be used in the SIMTAP plants. Resource and energy availability. We will analyze the environmental conditions, structures and infrastructure availability, of course, climatic data and topographic data, current land use and future zoning, and various types of constraints. So all that to, let's say, define a decision support system, which is useful to, let's say, support the implementation across the Mediterranean region of these SIMTAP pilots and future installations. Thank you very much for your kind attention, and of course, I would like to reply to all your questions, if any. Thank you very much.
Thank you, Daniele. Thank you. I saw a question in the chat, but I think it's about the animal welfare. So this may be a subject to be discussed at the end of the presentation.
Okay.
So I please now Dr. Giuseppe Coppola.
Yes.
In place of Jacopo Bacinetti.
Yes, thank you.
Anyway, Jacopo, I think is in the audience because I saw the name. It's difficult managing the audience.
No, but he is online.
Online.
I can confirm it.
Please.
Please,
okay. Thank you. Good evening, everybody. My name is Giuseppe Coppola. I am part of the University of Milan research team, and I am going to talk about the approach and the methodology we have adopted for assessing the sustainability of the SIMTAP systems. These activities were led by our French colleague of the EurAgEng. So, aquaculture systems, as our colleague from Turkey said before, is the fastest growing food production system in the world, and its role in feeding the increasing world population will be very important in the next years. Therefore, there is an important challenge of developing new and more sustainable ways of producing food with aquaculture systems. But what actually sustainability means? What does sustainability mean? The concept of sustainability, as we understand it today, is based on the definition of sustainable development given by the Brundtland Report in 1987, which defined development as the development that meets, that allows the current generation of meeting its own needs without compromising the ability of future generations of meeting their own needs. Therefore, there is this intergenerational element which is essential to the concept of sustainability. Anyway, our aim, the aim of the work package number five that we are conducting in this research project was to assess the sustainability of the SIMTAP system, to answer the question, how sustainable is the SIMTAP system? The development of this assessment posed us many challenges. Surely many methodological challenges. We had to take into account the different perspectives of the different stakeholders involved. We have to define, we have to choose which indicators and what kind of indicators to use, and many others methodological issues. But surely the biggest challenge was due to the fact that sustainability is a complex concept, is a concept that includes three dimensions which are often conflicting with each other, which are the social, the environmental, and the economic dimensions, the so-called three pillars of sustainability. Therefore, we needed a conceptual framework that allowed us to assess the sustainability of the SIMTAP systems while taking into account these three different and conflicting dimensions. And to overcome this challenge, we adopted a multi-criteria decision analysis approach. Multi-criteria decision analysis are approaches that are decision-making approaches, decision-making tools. They allow to evaluate various options, to order these options from the most favorable to the least favorable, while taking into account multiple and often conflicting criteria. They also allow to integrate objective measurements with the subjectivity by allowing the intervention of the people who are concerned with the decision. Many methodologies have been developed. We have decided to adopt the DEXI method. DEXI method stands for decision expert. It is a methodology that is being widely used since its conception in 1979 in different and various areas. It is a method for multi-criteria decision making, and it has three characteristics. It is hierarchical, it is qualitative, and it is rule-based. Now let me explain a little bit what that means. So in this slide here, we can appreciate how the general problem of the sustainability, of how sustainable is the SIMTAP systems, has been divided into a series of lower level layers composed by aggregate attributes. So we see how the general problem of sustainability has been divided into three simpler problems, the three economic, social, and environmental dimensions, and then how each of these dimensions, each of these aggregate attributes has been divided into another layer of simpler problems of other aggregate attributes, and so on and so forth, up to the input data. This way, a sustainability assessment tree is built, and the input data on the bottom of the model can be thought as the leaves of the tree. And the input data are basically the data that we are going to feed to the model in order to obtain the estimation, the assessment of the sustainability of the system that we are analyzing. Input data can be of various kinds, can be environmental input data such as greenhouse gas emissions, can be social input data such as the working time of the workers in the aquaculture facilities, can be economic data such as the selling price of the product. Input data can be either derived, can be either data that are just taken, technical, economical, or social data, or can be also estimated, calculated by the utilization of other methodologies, such as the life cycle assessment, the energy accounting, the life cycle cost assessment, the social life cycle cost, the social life cycle assessment, of which I will talk about later. So the DEXI method, as I said, is a qualitative method, qualitative model. Everything is scored on a qualitative scale that in this case goes from very low to very high. Input data are scored using threshold values, and the higher level elements of the sustainability assessment tree, which are the attributes, are scored through the utilization of utility functions. Threshold values and utility functions are defined, we have defined them by taking into account the interest and the perspectives of the stakeholders involved. And we have in the table here an example of how the utility function work, just to understand it. So this is the last step of the assessment when we have gained the score of the three aggregate attributes of the three dimensions, the economic and the social and the environmental dimensions, which are in the relative lower level attributes of the final score of the final overall sustainability attributes. And basically the utility function gives the score of the higher level attribute, in this case sustainability, given by the combinations of all the scores of all the the relative lower level attributes. Okay, so what have we? In this slide we can appreciate the activities that have been carried out so far. The activities started with an intensive literature review, where 413 indicators were selected among the indicators used in the literature for assessing the sustainability of aquaculture systems. Then this first draft of indicators was, from this first draft of indicators, 57 indicators were selected. Then the threshold values and utility functions, in order to give a qualitative scores to input data and aggregate attributes, were defined. And finally, a computerized version of the sustainability assessment method was developed. Basically, we have developed a template that will allow us to collect the inventory data that will either be used directly as input data for the DEXI model, or either will be processed by other methodologies and then fed to the DEXI software. So, as I said, the inventory data that will be collected through the template, some of these inventory data will be processed with four methodologies, with four kinds of analysis, in order to obtain other input data. These four kinds of analysis are life cycle assessment and the energy accounting for the environmental dimension, the social life cycle assessment for the social dimension, and the life cycle cost assessment for the economic dimension. In the next slide, I'm going to describe you each of these four methodology. So the life cycle assessment is a methodology that allows to estimate the environmental impact of a system, the environmental impact related to the life cycle of a product or a service, basically. The methodology is defined by two ISO standards, the 14040 and the 14044. And in this particular case, by applying it to the SIMTAP systems, we are going to consider the inputs that are such as raw materials or energy. We are going to consider also the process that are carried out within the SIMTAP system, and then also the outputs, such as the products that are produced, the emissions to the environment, the waste flows. And then through the life cycle input characterization phase, the environmental impacts divided into a series of impact categories will be estimated. The life cycle cost assessment clearly deals with the economic dimension. What we will perform is basically a cash flow analysis. We are going to consider, on one hand, the cash outflows, therefore the costs for buying the raw materials, the costs for the maintenance costs, and so forth. And on the other hand, the cash inflows, the estimation of the cash inflows, which are basically the revenues generated by the sales of the products. And then through the cash flow analysis, some economic performance parameters will be estimated, such as the net present value, the payback time, the internal rate of return, and the gross added value. The social life cycle assessment is a kind of analysis which is a bit different from the preceding two, because it is in a way less quantitative, it is more qualitative. The methodology is based on the guidelines published by the United Nations Environment Programme in 2019, and the aim of the analysis is to evaluate which social impacts are generated on the stakeholders considered by the activities carried out within the SIMTAP system. This evaluation will be performed by comparing data relative to the SIMTAP system's activity and some previously defined threshold values, or can be defined also reference values. Finally, the energy accounting analysis. The energy accounting analysis can be seen as an integration of the life cycle assessment in the environmental dimension, because it allows to estimate the consumption of biomass resources of the system expressed in the form of solar energy. In other words, the energy analysis allows to estimate the energy required directly and indirectly to produce something, in this case, the fish. So not only the solar energy will be taken in consideration, but also the energy included into the soil, the energy necessary to power the machinery, and also the chemical energy utilized by workers during their working activities. All these forms of energy will be expressed into the same form, solar energy, and then summed up. Then, just to give an idea of how the sustainability assessment tree is structured, this is the example of the environmental sustainability side dimension, or the branches of the environmental sustainability, and we can appreciate how the general problem of the environmental sustainability has been divided into a series of lower level layers composed of aggregate attributes. And then to the far right, there are the input data, some of which, as I said, will be estimated with the four methodology I've just described. Some words on the next activities that we will carry out in the future. Through the utilization of the template we have developed, we will begin the collection of inventory data of either real-scale aquaculture plants and of the experimental trials that use the SIMTAP systems. We will evaluate with the methodology I've just described their sustainability. We will gain a score, an overall sustainability score, and we will compare the two systems. Also, we will try to identify the so-called hotspots, which can be defined as the processes or the part of the systems which are less sustainable, and accordingly we will try to propose mitigation solutions. And in conclusion, I just point out that the methodology we have developed has been applied to a case study to a French salmon farm in this article that is currently in review. I am finished. I thank you for your attention, and I give the word to the coordinator. Thank you.
Thank you very much, Giuseppe. Very nice presentation, very, very clear. And we are a little bit late. There is a question in the chat about the animal welfare. It is an important issue, and indeed it is considered in the assessment of sustainability, because it is clear we eat fish, but we don't eat them. So I don't know if Daniele would like to reply to the question, or maybe more other colleague, more expert on animal welfare. For instance, Ubaldo.
I would start reading the question, okay, which says let's say the question popped up when I was talking about probably the possibility of understanding the conditions where fish grow during my presentation, because the question says, in the initial part, you also talked about animal welfare. I wanted to ask how you can use the data collected with your integrated monitoring system to evaluate parameters related to this topic, and if you're planning this type of assessment. So I can just tell something, and then of course Baldassare, maybe you can add, let's say, more relevant things, and anybody else. I can say that, let's say, of course, when we monitor each, let's say, the production performance of any livestock, included fish, we can, of course, evaluate survival rates, growth rate, etc. But let's say, thanks to the monitoring system, we can measure and keep a recording of the conditions in which the fish grow and were grown. And I think that this is important for a number of reasons. For sure, for example, Joel was talking about some unexpected weather conditions and let's say environmental conditions which caused an increase in fish or other animal, let's say, death. Okay, so we can have unexpected environmental conditions, and if we have the possibility to trace in real time the conditions where the fish grow, I think that, for example, we can try to develop some solution and further improvement of the facilities themselves. So let's say understanding the conditions which may cause problems in animal growth, for example, can be useful in further improving the system. And second thing, I think that this is, I think, valid in general, not only for fish, of course. If we can provide objective data about the conditions where animals were grown, I think that this could be useful also on the market, because if people can be aware in an objective way of the conditions where animals were grown, I think this could be, let's say, can be part of the traceability topic. Okay, so I think that the system can support these things.
I may add something, and mainly in relation to what Daniele just said, is that people should be aware of which conditions are the best for fish growth, and unfortunately, very frequently people doesn't know that. But experts know very well where fish, the conditions in which fish can grow as best as possible, and because these conditions are those in which fish welfare is ensured. Okay, because if we do not provide to the fish the best conditions possible, we will never get the best growth performances. From this aspect, from this point of view, yes, I hear someone with the open microphone. Okay, that's fine. If we are not able to provide the fish the best conditions, we will never get the best performances, okay, of the fish. So from this point of view, there is how can I say, the same goal between farmers, aquaponics people, and the fish, of course. This is, in my opinion, is quite a general rule. Of course, there are some small exceptions, but in general, this is true. What we can do, or what we do within the SIMTAP, surely we are monitoring the conditions in our systems. We know which conditions are best for the fish growth, so we compare this data with the standard data we know, and we check if some parameters recorded in our condition doesn't match with the best, with the optimal, and subsequently we can work to improve these parameters within our system. This is what we do first. Secondly, we observe the fish. Fish behavior is a very important parameters for fish welfare, So we every day check the fish behavior, okay, when we feed the fish, when we clean the tanks, when we check mortality, when we manage the system, always we get some information about the fish welfare. What we are not thinking, we didn't think to do is to make direct measurements about fish welfare, because are costly, time demanding, and in this moment we can use the indirect parameters to ensure to check for fish welfare. So what we are not doing is to get some samples to check for cortisol analysis, for example, because the cortisol level in the body or in the blood may be an interesting parameters to check for stress. Let's say stress level in the fish. But at the same time, at the moment, okay, I don't know what's happened in the future when we go ahead with our project, but at the moment we don't have any concern about fish welfare other than the water quality that we measure every day or weekly to maintain standard conditions. So this is what we do about fish welfare, and we are not going, at least at the moment, to measure directly fish welfare through determination, analytical determination on the fish.
Okay, thank you, Waldo. Hussein?
Thank you, Waldo. You addressed very well, but I would like to add two more issues concerning with the welfare, fish welfare. In rainbow trout aquaculture, fin erosion is used as index of welfare, and I think the same issue can be transferred to the sea bass and sea bream. The second important factor to indicate welfare is the scale shedding or scale integrity of fish. Therefore, from the appearance, we can develop some kind of index, and then we can measure so-called fish welfare, or compare our fish in terms of those indexes to conventional systems. Then we can make some comments about it.
I totally agree with you. You're saying, in particular, when we use high stocking density, in that case, fin erosion, it's the normality. So that is one of the parameters that we check every time we weigh the fish or manage the fish to avoid such kind of situations. Right. You are right.
There is a comment in the chat on stock density.
Basically, the comment says that we should not forget that raising fish at high densities is a con, so it's not good for fish welfare, basically.
Yeah.
Yeah.
This is, this is always a matter of compromises. Okay. From one side, we have to care about fish welfare, of course. At the same time, we have to carry out an economically sustainable activity. Okay, so of course, this is the compromise we have to find. Absolutely, yes. We really know that high stock density is very, very stressful for fish. And when mortality rises, we soon realize that, and of course, we lose money. So this is, of course, one parameter that we consider when we manage an aquaponic system, as well as, of course, cages and other tanks.
Okay, thank you. Indeed, we received some comments about the project. For instance, that the stock density should be as high as possible, but this is at the cost of animal welfare.
Right.
Okay, so if there are other questions, please switch on the microphone or use the chat.
Yes, thank you very much.
Thank you.
Actually, I would like to say thanks for sharing this scientific information. I mean, a kind of pre-scientific information even, but it's available, I guess. By the way, I want to share my thinking style as a sustainability issue. Sustainability, I guess, is a synthetic ethic because sustainability cannot be applicable all sides of the life, I guess. Just I want to share this information, including synthetic ethic assessment. Thank you very much again.
Thank you. You are welcome. And so I think we can. What do you think, Daniele? We can conclude the webinar? Okay.
Yeah, I think so. I would like to thank the organizing committee of the EurAgEng conference once again for allowing us to be within the program of the 2021 EurAgEng conference. It was an honor and a pleasure for us. And yes, the floor is yours for the conclusions, Alberto.
Okay, thank you, Daniele, and of course, thank you to all of you for attending this webinar. Thank you, Daniele, for the technical organization, and of course, thank you to the European Society of Agricultural Engineers. And just a technical information. All the webinar have been recorded, and after some editing, it will be available on YouTube, and you will find the link in the project website. And again, I thank you very much, and best wishes for your work and your family. And see you around, hopefully.
Bye-bye, everybody.
Bye-bye.
Thank you.
Bye-bye.
Take care.
Thank you. Bye-bye.
Thank you.
Thank
Bye-bye.
you. Thank you.